Okay, let me start by recapitulating a little bit about what we have learned about the small strain tensor. The small strain tensor is basically defined by this relation here, which is known as the strain displacement relation. In indicial notation, which we are going to use quite extensively, the strain displacement relation is this, defines 9 components of the strain tensor, but from this relation we can easily figure out that if we switch I and j here, uh, this becomes j comma I and this becomes I comma j, therefore epsilon ij is symmetric. So this is a symmetric tensor which um, has 6 independent components and can be written as a symmetric 3 cross 3 matrix. So sometimes we are going to use non-indicial notation. So in place of u1 we are going to use u, in place of u2 we are going to use v, and in place of u3 we are going to use w, and x1 will be replaced by x, x2 will be replaced by y, and x3 will be replaced by z. This is also true about many books that don't use indicial notation for teaching you elasticity. And we will do this especially in cases where we do two-dimensional problems later. So when we do this, if we remember this mapping, this is the matrix form of the small strain tensor in Cartesian coordinates. So epsilon 1 becomes epsilon xx, which is this. This is epsilon xy or epsilon 1 and so on. So it's a symmetric 3 cross 3 tensor matrix containing the components of the strain tensor in the Cartesian system. Now these are the 6 components which are independent. These are the 6 components which are independent, and sometimes we use things like gamma xy, which we define as 2 epsilon xy. So we use this for the shear strains. These are the shear strains. These are the normal strains. These are the normal strains, and these are the shear strains. And when we use this 2 here, we call it the engineering shear strain. The engineering shear strain does not form a tensor. So when you do tensor transformation, which we are going to learn today, you don't use the engineering shear strains, and if you're given engineering shear strains, you need to divide by 2 to get the tensorial shear strains and then do the transformation. So if you use engineering shear strains, then the tensor whose Cartesian components are represented by these quantities, the symmetric tensor whose Cartesian components are represented by these quantities, if you use the engineering shear strain in place of these 3 numbers, you are not going to get a proper transformation. That's why it's important to distinguish between the indicial shear, tensorial shear, and the engineering shear. We can write these equations in cylindrical polar coordinates, and we will often do problems in cylindrical polar coordinates. So when we write it in cylindrical polar coordinates, we have to remember how we do the transformation from Cartesian to cylindrical polar. The transformation of course remains exactly the same. We deal with the base vectors in exactly the same way that we have learned, and we again get a symmetric tensor which has which has 6 independent components. And now the mapping that we use is we call u1 as ur, u2 as u theta, u3 as uz, sometimes we'll call it u3 as well. X1 is of course r, x2 is theta, and x3 is, we'll sometimes call it x3, sometimes call it z. So as we know that x1 and x2 are different from the Cartesian system, x3 remains the same. So in the cylindrical polar coordinate system, these turn out to be the 6 components. Again, if you use, in place of this, if you use 2 epsilon r theta, we will call it as gamma r theta, and that would be our engineering shear strain in the cylindrical polar coordinate system. Now, we have also looked at the physical significance of the components of the strain tensor. And for example, take one of the normal components, del u1, del x1, and we have figured out that it is the relative change in length of a line which was initially located along the x1 direction. So that's AB in our case, and the relative change is A prime B prime minus AB divided by AB. So this is the change in relative change in length of a line which was oriented along the x1 direction. Similarly, del u2, del x2, the other normal strain, would be simply B A prime D prime minus AD divided by AD, and u3 x3, in this case it's has not been drawn, it's a 2D picture. So u3 x3 would be the relative change in length of a line which is oriented initially along the z direction. The engineering shear strains, for example, gamma 1 2, which is 2 times epsilon 1 2, we know that, is actually the change in this angle. So it is the change in angle between 2 lines, one oriented along the x direction and one oriented along the y direction. The angle between them initially is of course 90 degree. So this 90 degree angle minus this beta minus this alpha angles, which are supposedly small, gives you the engineering shear strain. Half of that is the tensorial shear strain. Similarly, any other shear strain would give you the change in angle, that is 90 degrees, between 2 lines that are oriented along x1 and oriented along x2, or oriented along x2 and oriented along x3, or oriented along x3 and oriented along x1, to give you the engineering strain components gamma 1 3 and gamma 2 3. Okay, so this is the physical significance of the small strain tensor. And now, because it's a tensor, what we can also do is transform the components of the strain tensor. The transformation would go exactly like any other tensor. In fact, the transformation for stresses, when we learn about stresses, would also be exactly the same. So we will stick to our conventions. Our convention is that when we determine Q, so when we determine Qij, we take cos of old to new. So we take cos of Ei Ej prime in this case. So this is the old and this is the new. You have to define which you think of as the old and which you think of as the new. So we define this angle theta for a 2-dimensional situation. We define this angle theta, which is cos of x1, that is the old, to x1 prime, that is the new. So when you do this transformation, uh, what exactly we are doing is we can look at this from a physical point of view and say that okay, when we were working in the old coordinate system, this was our pillbox in 2 dimensions with sides dx1 and dx2, and suppose after deformation it got into this shape. Now I have changed my coordinate system to x1 prime, x2 prime, which means that now if I have to define my strains in this new coordinate system, I'll have to start with a pillbox whose edges are oriented along the x1 prime and x2 prime directions. So this is the pillbox that I'm going to use, whose edges are now oriented parallel to the x1 prime and x2 prime directions, and the deformed shape of course remains the same. So the geometric connection between this pillbox with edges parallel to the x1 prime and x2 prime directions and the deformed shape, the geometric connection between these two, this rectangle and the quadrilateral that results after deformation, gives me the transformed strains in the x1 prime, x2 prime direction. In general, this would be my Q matrix in the Cartesian system when I'm going from old x1, x2, x3 to new x1 prime, x2 prime, x3 prime, which in tensor in matrix form is written in this manner. Because we are using old to new, we are getting Q transpose epsilon Q. If we had used it the other way around, as many books do, we would get Q epsilon Q transpose. So you should be careful, but you don't need to be very careful because epsilon and epsilon prime both are symmetric tensors. So even if you do Q epsilon Q transpose, you will get the same answer. But anyway, this is the form that is consistent with our definition of Q, and this is what we are going to use. Again, the form in indicial notation is given here. We define Qij as cos of xi xj prime, and this is my transformation relation. Especially in 2 dimensions, this is the transformation matrix that we get, where theta is the angle that I showed between x1 prime and x1 axis. So it's also the angle between x2 prime and x2 axis. So in 2D, it takes a very simple form, easy to remember: cos theta sine theta minus sine theta cos theta. There's no transformation in the 3 directions, so this is all zeros except this, which is 1. This we had derived before, and this is what we will use for 2-dimensional transformations. For 3-dimensional transformations, you have to use this. Remember the order of the indices. These are the old components Mn. These are the old components, and these are the M comes first, I comes next, N comes first, J comes next. So all the Q's have the indices of the old component first and the indices of the new component after that. So if you had used a reverse convention here in Q, then this will be IM and JM. So you can use either, but you have to use it consistently. Okay, now let's do a problem which involves transformations of strains. Now suppose I have a plane, a sheet metal, which is being formed, and on this sheet metal, as it is being formed, I want to measure the strains. I don't have any strain gauges, about which you are going to learn towards the end of this week. I don't have any strain measuring instruments. All I have is a scale. So that's what I have to use in order to measure the strains that are happening on the surface of the sheet metal as it is being formed. So what I do is I put 3 indentation marks on the sheet metal. So this forms a right angled triangle, and I put two axes x1 and x2, and I measure the distance between these indentation marks. After deformation, the indentation marks take a different position, and again I center my axis at one of the indentation marks, let's say A, and draw x2 and x1. I can do this because remember, in order to measure strains, what I am interested in is the relative distance between points and not the absolute distance. So the fact that the point A has moved from here to here does not bother me. I always take the distance between A and B and A and C, and I don't bother about the relative displacement of A. So now the normal strains are easy to measure. So when I measure the normal strains, I just remember that when I am measuring epsilon 1, I have to take a line which is initially oriented along the one direction, that's this line, and take its relative change in length. The changed length is 1.5. The initial length was 1, so the relative change in length turns out to be 0.5. Similarly, when I take epsilon 2, I have to remember that I have to take a line which was initially oriented along the two directions, look at its change length, that is 2 centimeters from 1 centimeter. So the epsilon 2 strain component in this coordinate system is equal to 1. Now you might contend that these are very large strain components, which they are. These probably don't qualify as small strains. Just to give you an idea, though it's not connected to this problem, the yield strain of most materials are of the order of 0.02. So this is for ductile materials. And in the elastic range, the strains that we will measure in experiments that we are going to do towards the end of this course would be of the order of 10 to the power minus 6 to 10 to the power minus 5. So that's what small strains look like. So these definitely don't look like small strains, but that's not the point. We are just looking at the principle. Now I have only one shear strain to worry about, that is epsilon 1, 2, and I know that this is gamma 1, 2 by 2, and I know that gamma 1, 2 can be measured from a change in angle. So what do? I take two lines that are oriented along the x and y directions, 1 and 2 directions. The angle between them is 90 degree, and I measure the changed angle between these two lines. Now, of course, I can do this, and you can see that it's an increase in the angle. So the shear strain epsilon 1, 2 is likely to be negative. However, I suppose I work in a really bad company, really bad plant, where I don't have anything other than a scale. I don't even have a protractor. I can't measure angles. In that case, what I'm going to do is I am going to use one more information that I have. So, for example, if I orient axis along this direction, so let's call it x1 bar and let's call it x2 bar, then I actually know epsilon 2 bar. How? Because I can take a line which is initially oriented along the 2 bar axis, and its changed length is known to me. So I can take epsilon 2 bar as the change length is 2.8. The initial length of a line oriented along the 2 bar direction was 1.414 divided by 1.414 would give me epsilon 2 bar. That's what I'm going to do in the next slide. So if I do this, again I get epsilon 2 bar, which is again rather large, but we don't worry about that. So now I have three information. I have epsilon 1, I have epsilon 2 2, and I have epsilon 2 2 bar. And now I use my old friend, the tensor transformation, using this convention that we go from old to new while calculating Qij. So the old axis EI to the new axis EJ, that's what we do. Okay, so if we do that, this is the tensor transformation relation. I know epsilon 2 2 bar, so I want to connect epsilon 2 2 bar to the other strain components in the x1 x2 coordinate system. So 2 2 bar is in the x1 bar x2 bar coordinate system. This I know, and this I want to connect. So when I do that, I do m and n both equal to 1, so I get q12 12 epsilon 11, q12 q22 epsilon and 12, and there's a 2 here, and q22 q22 epsilon 22. So I take m and n to be 1 to be 1 1, to be 1 2, to be 2 1, and finally 2 2. And this 2 1 and 1 2 cases both give me the same number, and that's why this 2 comes into. Okay, so once I use this, I realize that this is the only thing that I don't know. Everything else is known to me. I have this information. I have information about this. I have information about this. And of course, I know the Q1 to Q2 and so on. I know the whole Q matrix because I have done the coordinate transformation. I know it's a 45-degree transformation. So it's 1 by root 2, 1 by root 2 minus 1 by root 2, 1 by root 2 kind of a matrix. So use that information and we can get epsilon 1 2 out. I think I have done the calculations correctly. So if you do it correctly, you get epsilon 1 2 to be equal to minus 0.46, a negative value, which is what we expected because it was an increase in angle rather than a decrease in angle. So that's why epsilon 1 2 turns out to be negative. The engineering shear strain, of course, would be twice of this. Again, let me tell you that these are rather large values, but it's just to explain a principle of how we use the basic idea, the basic physical concept behind the components of the strain tensor in order to calculate them. I will stop here and we will take up a new topic in the next lecture.